Okay, going live now. You're live.
Recording in progress.
Okay, going live now. What?
Okay, we're live. Yeah.
Why do I hear myself?
Oh no, because I need to mute it on my side. You're good. You're good.
Okay, cool. Hello, everybody, and welcome to another exciting episode of Quirkcast. I'm your host, Mikey.
And this is Sahil. Welcome, everybody, to a brand new, exciting episode of Quirkcast, where few logistical things. Our host Tim may or may not be able to join us, so if he pops in, be a pleasant surprise. But if not, all good. And in addition to that, a few other things is that if you haven't joined our Discord channel, do join it there so you can ask us questions during the ask us questions and we can get to that. As well as we do this if you're watching on YouTube, where we do this every Tuesday, or try to do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern. Do ask us questions during the episode. So without further ado, let's get to it, Mikey. So Mikey, we've been talking a lot about different issues in physics, different problems and whatnot. But I think one thing that contains a lot of mystery itself, which I don't know if most people think about, is like empty space, or as if this notion of nothingness, as if space is empty itself and there's nothing in it. So maybe you can walk us through kind of the evolution of how this evolved in terms of the thought process behind the notion of empty space, starting from high school physics and then showing that it's a bit more complicated than people think it is.
Yeah, sure. So I guess if you look at the history of the history of how people thought about empty space prior to the advent of quantum mechanics, right? We had this picture where space is kind of like an empty canvas, and you can paint on this canvas the stuff that fills this canvas, you can think of them as particles. And prior to quantum physics, we thought of them as basically like little marbles or little Lego blocks that make up everything. So it was thought that if you just took a box and you just removed all the matter from it, that box of physics called quantum mechanics. And quantum mechanics introduces kind of an interesting twist on the idea of empty space, because it says that there is no such thing as empty space. You can't have completely empty space. There's always some probability of measuring something in that space.
Mm-hmm. I guess how does quantum mechanics sort of play in? Because why is it that I just can't remove everything from the empty space itself? What stops me from just removing?
Yeah, the heart of why quantum mechanics predicts that there's no empty space is something called Heisenberg's uncertainty principle,
Mm-hmm.
which means that it's impossible to precisely measure either the position or the momentum of a particle or anything like that. So what that means is that, let's say I have a particle of light, right? And I have a particle of light just stuck in a box, let's just say for the sake of argument. One way that you could make that box empty, I guess, is if you took the light wave and you stretched out its wavelength until its energy got down to zero. Then you have a zero energy particle, which is basically like saying the particle doesn't exist. And that will be one way to create empty space. But the uncertainty principle says that the energy can never be exactly zero. You can never actually take away this particle of light and completely remove it. There's always some probability you're going to measure some amount of energy associated with it. And you can actually measure this. People have tried to create perfect vacuums, perfectly empty boxes. And because of the uncertainty principle, there's always going to be a little bit of bubbling of energy inside there.
Mm-hmm. I guess then, could you walk us through maybe at a high level what these experiments look like in terms of how do I know that there's something in the box, or like this empty, if I try constructing empty space, like what does that experiment sort of look like?
I guess the most famous experiment that people have done, the way they measured the energy of empty space is through something called the Casimir effect. So people have
Mm,
actually gone to outer space and created perfect vacuums or close to perfect vacuums, and you can
mm,
take two metal plates and you can put them very very close to each other, and if you work out the equations of quantum mechanics, it actually predicts that this energy of empty space will cause a small amount of attraction between these two metal plates.
mm.
And you can actually measure that in an experiment. Um, I
I
think,
I see. Well, okay, so I don't know if you know the answer to this, but like, why would there be an attraction between the two plates?
okay, so it has to do with like if you have two empty plates,
Hmm.
quantum mechanics says that the vacuum, you can think about it as kind of like a waveform, and there's a certain number of waves that can fit in between the two plates, and there's a certain number of wavelengths that can fit outside of the two plates.
Hmm.
And this causes some small amount of pressure that causes the plates to attract. If you believe this model,
Oh, I see. So it's like it's more of a pressure argument more than like a charge attracting charge kind
yeah,
of argument.
yeah, definitely, yeah.
Oh,
Uh-huh.
I see, I see. Okay. Okay.
I
I
think it
can
also be worth it to maybe talk about like just the picture of the universe that quantum mechanics kind of paints. I think it'll make it a little bit more clear. So
Mhm.
we're used to thinking of particles as like little hard marbles that fly around. Um, but one thing you can do is you can create like you can create particles out of nothing almost.
Mhm.
And the picture that quantum mechanics paints for how this happens is that you imagine that empty space is full of this substance called a field.
Mhm.
Um, so for each particle, there's an associated field. So for the electron, there's an electron field permeating all of space. For quarks, there's a quark field permeating all of space. And if you
Mhm.
want to create an electron, all you have to do is basically smash that region of empty space hard enough with something, and then electrons pop out. So, electron, the particle, is really just a vibration of this thing we call the electron field, which permeates
Mhm.
all of empty space. So, if I have an empty box, one way in which it's considered not totally empty is that there is a field inside of there. So, even if there's no electron particles in the box, the electron
Mhm.
field is still permeating through it.
Mhm.
And I can create an electron just by, creating a vibration in that field. And what quantum mechanics says is that this field is never vibrating completely zero. There's
Mhm.
always some minimal, imperceptibly small amount of vibration in this field. And that's
Mhm.
one way to think about the energy of empty space.
Oh, I see, I see. So it goes even beyond the argument that you could make that like, the universe is full of stars, those stars are emitting photons, so there's no such thing as empty space in the universe because it's filled with like these low energy photons, or or some level of photons.
Yeah.
But if you were to remove all the photons, like hypothetically, it still wouldn't be empty space. There'd still be like stuff in it, or not stuff in it, but there still would be energy in it. Is
There would
that
still
fair
be
to
a
say?
photon field, yeah. So, one question is you could ask is like, what if I just remove all the fields? What if I could have a box and I just remove all of the quantum fields inside that box? Um, maybe there's a way to do that. It's just it's so far like these fields that I'm talking about,
Huh.
they permeate all of space in a way that it's not even conceptually possible to think of removing them, or they might even just be part of space itself. You can think about them as sort of
Yeah.
being, yeah, making up space itself. If you were somehow to remove the fields from this box, you would be changing the nature of space itself.
I mean, I don't think you would have space, right? Like if you were to remove the field that corresponds to gravity, for
Yeah,
instance, like
yeah,
you wouldn't have space time as we know it at the
yeah. This
moment.
is a totally like a hypothetical like
Yeah.
Like there's that's absolutely true. Yeah, if you were to remove all of the fields from an empty box, that would be like saying you're removing space itself from the box.
You're moving the box from the box.
Yeah.
I see. I see. That makes sense. So, okay, so coming back to this, so there are these quantum mechanical fields. Basically, can I think of them as kind of like really loosely speaking, like like an ocean of like waves, and like these waves have different types of properties. They have some have charge, mass, spin, all these intrinsic properties, and they permeate the entire universe. Um, and essentially, if I want to produce one of these particles that correspond to one of these fields, like you're mentioning, the electron field, there's this very like low energy, imperceptibly small kind of like wiggling of this field. I just need to smash a region of space with a high enough energy to be able to create that. Is that a fair enough
Yeah,
statement?
actually, I think that's a good analogy. Yeah, you can kind of think about it as like the space
Mm-hmm.
we live in is kind of like we're swimming in water.
Mm-hmm.
Um, and if like what we used to consider empty space is like filling a box with water that is perfectly motionless, no waves at all in the water. And what
Mm-hmm.
quantum mechanics tells us is that you can't have water with zero waves. There's always some jittering vibrations in this water. Um,
That makes sense. That absolutely makes sense. I okay. So if we go with this like water analogy, it's kind of like if you take the water out, there's no universe basically as we know it, or maybe not even a universe to even begin with. So going to this thing, I guess like what are the implications of this? Like implications that empty space has like energy in it. Like what does that allow us to do? What like counterintuitive things come out of that?
well, the most important function of so the most important function of the fact that empty space has energy is the fact that the energy of empty space actually creates space.
Oh,
Yeah,
oh,
it's one of the most like that's why empty space has energy. The universe we know is 13.8 billion years old.
mhm.
It had a beginning. It had a point in time where the
Yeah,
universe was created, and one of the things that has to happen when you create a universe is you have to create space. The
yes.
universe is expanding right now, and
Hmm.
what we mean by that is that space is constantly creating more space. Um,
Wait, before you go further, I want to kind of double click on that. How do you know that like more space itself is being created, not that like things are moving like away from each other? With this like this space that's already like given, that's just there, and then like things are moving farther away from each other.
within that space, well, if everything is really moving away from everything else,
Yeah.
um, you're saying as opposed to like space being static and everything rushing away from each other versus space itself stretching. Is there any experiment you could do to distinguish those two things? Are they not completely equivalent?
Yeah, I mean, so okay, so to kind of like, I guess one thing is that in these sort of observations, like it said that things at a far enough distance are receding away from each other faster than light. But I guess like that begs another kind of this is more like conspiratorial kind of like questions in some sense. Like, how do we know that like relativity is followed at like really, really large distances? So like for instance, like why can't you have it be such that like things are moving away from each other faster than light at a certain distance?
Wait, that is what relativity says. Uh, I'm
Oh
not.
no, no. Relativity says that information can't be exchanged faster than light.
Yeah, yeah, but relativity also predicts that the energy of empty space causes space to stretch. But wait, sorry, to go back to your original question, the reason why we're pretty sure that space is stretching is because of exactly what you just said, actually. If you look out, you see everything's moving away from each other, right?
Yeah.
And things that are farther away from us are moving away faster.
Yeah.
This is the kind of behavior you would expect if you imagine that space was just stretching uniformly. If you imagine that everything is just rushing away from each other,
Yeah.
you'd have to explain. Wait, yeah, I guess it would be the same. Yeah, that would also imply that things that are farther away are moving faster.
Yeah,
Um,
okay, like kind of like in addition to a gravity field, there being like a quote unquote anti-gravity field where it's small, but it like behaves on behaves much more strongly on larger, like really large distance scales, like immensely long distance scales, longer than like galaxy length type of scales, but like even further than that. And so I wonder like what is the problem with doing that? And if you don't know the answer, that's totally fine, but just kind of want to pose that question.
yeah, I don't think there's necessarily a problem with it. I guess the question is, what does it gain you to imagine that there's some new anti-gravity field when you
Hmm.
can simply just it's a much simpler assumption to assume that space itself is just stretching uniformly, and that would explain everything that we see perfectly. That would explain the fact that things that are farther away are moving away from each other, are moving away from us at a faster rate than things that are closer. It just fits the data so perfectly. Plus,
I see.
Einstein's theory of relativity predicts that space should be stretching by some uniform amount. So you
I
could
see.
you could you could say, okay, well that's well and good. Maybe Einstein's theory is wrong, and there's actually some anti gravity field.
Mhm.
Um, but I can't think of anything that you would gain from that. And I'm sure there would be problems with it cosmologically,
Mhm.
or because like the idea that space is stretching and the fact that that explains why things are receding from us, that not only matches the observations we see today, but it also matches with the entire history of the universe that we've seen. So whatever anti-gravity theory you came up with would have to essentially behave exactly like stretching space.
I guess like okay, this kind of okay. Maybe this is going slightly the realm of philosophy, or like I don't know if you want to call it philosophy. Yeah, I'm not sure what branches would fall under. But like, if space is expanding, like, what is it expanding into? Like, is it just because one question that comes up is if you like already have space that exists and things like let's say a quote unquote infinite amount of space or near infinite, and the things are just moving away from each other. There's nothing like it's expanding into, but like this notion of like what is the space like? Yeah,
The
what's
space
it?
beyond the space.
Yeah.
um, yeah, we don't have a good answer for that, because everything as far as the eye can see, all we see is space.
Yeah.
What kinds of things can it be? It could be expanding into more space. You do have these theories where you can have space creating when like two higher dimensional spaces collide with each other and create like an intersection, and you can
Mhm.
imagine that our space is that intersection, and
Mhm.
as they continue to collide, that intersection grows. So
Mhm.
that's one picture, that space is just expanding into another higher dimensional space. But then you can ask, what do those spaces live in? And it's kind of like turtles all the way down.
You read my mind. I was just thinking about that expression.
Yeah.
Uh, okay, so let's say it is like the more simplistic theory, simplistic in terms of a simpler explanation for spaces expanding. I guess like one question. I guess one question that I have is what was it? I had and then I kind of lost it. I guess like maybe we can give the audience a sense of scale of like how fast is this expanding, or like what's kind of the deal around that? Is it
Great.
slow? Is
Yeah.
it like gradual? What's yeah.
So yeah, yeah, that's actually what I wanted to talk about next as well. Is so it's kind of a funny thing, right? Like we said that empty space has energy in it, right? And
Hmm.
that energy causes that space to grow and stretch. But
Mm-hmm.
when the space grows and stretches, you're creating new space. You're creating
Mm-hmm.
more energy.
Yeah.
So it's actually a process of energy creation.
Mm-hmm.
So the energy of empty space causes space to expand. Since empty space has energy, you're creating energy that causes the space to expand more.
Mm.
So this is
Actually,
why the energy of empty space not only causes space to expand, but it causes it to grow exponentially.
mm,
Because there's this feedback loop where you stretch the space, creates more energy, creates more expansion, creates more energy, creates more expansion, and it's exponential. So um, the way that the energy of empty space causes space to expand, yeah, results in this accelerated expansion. And in
mhm.
2012, the Nobel Prize was actually given to astronomers for measuring very closely the fact that, yeah, actually, not only is space expanding, but it's expanding at an accelerating rate, exponentially accelerating rate.
I see. I see. Before we talk about this, the speed of expansion, I just want to kind of double click on this notion of like space expanding and then creating more energy, which causes it to expand more, which creates more space, which means there's more energy.
Yeah.
Like I would have expected, from my like human level intuition of everyday experience that like, if I take some material and I stretch it out, it's like density and
It's diluted.
energy like per unit volume or whatever gets smaller.
Yes.
Why is it that like this stays constant or like, why is it that it doesn't go down as you stretch it? Like, is there any?
That's yeah, the fact that the energy of empty space does not dilute, that is the defining property of the energy of empty space. Um, every single other type. So if I have a box and I have some particles in it, and
Uh-huh.
I make the box bigger, then the energy from the particles will dilute, just as you said. It basically, as you
Hmm.
stretch the material, and the density of the energy, you'd expect it to go down
Uh-huh.
as you stretch out the box.
Uh-huh.
And the type of energy that dilutes, like the energy from particles, that
Yeah.
causes actually like a decrease in the expansion because
Yeah.
the energy itself is diluting.
Yeah.
Um,
Yeah.
uh, but the energy of empty space, it, it doesn't dilute because it is the intrinsic energy of empty space,
I
right?
see.
Yeah.
I see.
Um,
So,
so it, like
uh,
the entire expansionary history of the universe is sort of a battle between
mhm.
these two types of energy, and for most of the history of the universe, the expansion was not accelerating because there was so much stuff inside the universe that the dilution of the energy was actually causing the expansion to slow down.
Mhm.
But as time goes on, the amount of energy of empty space starts to far outweigh the amount of energy from other stuff in the universe, and you start to see this accelerated expansion, and that's what we observe right now.
I see. So kind of double clicking on that. If we look at empty space, I mean, there are all these like fluctuations of particles popping in and out of existence, kind of this like quantum soup, as I've heard it called. Like, yeah, just lots of fluctuations. And these correspond to particles. And there's also these like quantum fields that are there that also correspond to particles if you were to whack them hard enough with a certain strength of energy. But like, if that's all there is in empty space, I would expect as you stretch out empty space, those would also like get stretched out, which means they would get diluted further. So is there something else in empty space that's not being accounted for based on like these quantum fields?
Well, particles definitely get diluted
Yeah.
but the substance, the fields themselves. Yeah, I guess you could say that as you're expanding space, you're actually
Uh-huh.
creating more field.
Wait, so like the fields themselves, these background fields don't get like, I don't know, don't get like stretched out even further. They just kind of like just create more of themselves.
Yeah, yeah, you literally create more. So I guess to go back to the water analogy, like,
Yeah.
yeah, as I expand suppose I have a like waterways. As I expand the box,
Yeah.
those water waves will stretch, just as you said.
Yeah.
But as we're stretching, we're basically adding more water to the box. So the amount of the small, if I discount like the actual waves that we see, the jitter of the
Yeah.
waters, that's the amount of that is increasing. So it's like you're expanding a box through the water almost.
Oh, I see, I see. What remains the same throughout this expansion? Is it like the energy density per unit volume of empty space on average remains the same as space expands, or like what or does it go up, or like what's
No,
the
it
deal
stays
with that?
constant. Yeah, yeah. That's
Okay,
actually
okay.
why. So the technical term for this is actually the cosmological constant.
Oh, okay, okay, okay. That's been attributed to this quote. I don't know who said it. I don't know there was Einstein or
Linus
whatever, but
Paunder or
it's
whatever.
Leonard Einstein. Yeah,
Yeah,
that
yeah. He
that
didn't like
quote.
this idea. No, I mean, like, I think you're right to harp on this. It's the most puzzling feature of the energy of empty space. The fact that it doesn't dilute as you stretch the space is
Yeah.
what literally what makes it special. It's what gives it the function of creating more space. So
Mhm.
whoever designed this universe designed it in such a way that it has this mechanism that
Yeah.
creates it's a recipe for how to create space, and that
Uh,
recipe relies on the fact that this energy of empty space does not dilute itself. You create space, you're genuinely creating more water.
I see. So, would you say this violates one of the sacred principles I learned in physics back in like high school, conservation of energy?
Oh yeah, energy is not conserved on cosmological scales at all.
Okay, okay, okay.
Einstein's theory directly predicts that energy should not be conserved if you look at the whole universe, exactly precisely because of this fact.
Uh, so okay, before I get to the rate of expansion, I know you want to talk about it. The last question I want to ask you about it
Oh, we don't have to
is,
talk about. We can say that for next week.
oh, okay. But you seem excited to talk about it, so I just want to bring it up. One question I have is, oh, yeah, I forgot what I feel like I have the question in my mind and then I lose it. The mechanism around this expansion, is it understood, or like, this like adding more water as the universe expands, or is it still like a giant mystery of like how that even happens?
No, that's totally well understood. Yeah. Yeah, there's no mystery about that. The only there is a mystery surrounding what the energy of empty space should be. That is probably should be saved for another episode.
Okay.
But like the theory, just to say it very quickly, the theory actually predicts that this energy of empty space, these little jiggling fluctuations of the
Mhm.
water that we can't
Uh-huh.
avoid, the theory actually predicts that those should be very large. But when we
Mhm.
observe, we actually observe them to be very, very, very almost imperceptibly small. Um,
Hmm.
and that's kind of a mystery, but it's a mystery that's very tied to our existence because the fact that the universe is nice and smooth and expanding at a reasonable rate relies on the fact that these fluctuations of energy in empty space that those are imperceptibly small.
I see. I see. So just summarize what you said. We don't have to dig into it. We can save another episode for it. But theory predicts that like the energy of empty space would have like these large like quantum field waves. I
Yeah,
don't know. Like imagine like the ocean was like very violent.
yeah,
What we actually observe is that the ocean is like,
very peaceful.
figuratively speaking, very calm.
Yeah. Mhm.
Okay, okay. That is interesting. Yeah, I would definitely like to dig into that in
Yeah.
another episode.
But aside from
So,
that, though, like just to reiterate the answer to your question, yeah, like theoretically, if you ignore that issue of
mhm.
magnitude,
Yeah,
everything
yeah.
is very well understood. Einstein's theory predicts that empty space energy will cause the universe to expand. Quantum
Mhm.
mechanics predicts that empty space should have energy. So it all works together very, very beautifully. The only thing that's confusing is the magnitude of these fluctuations and the magnitude of the expansion.
Gotcha, gotcha. I guess like wait, so okay, so it's explained by theory. Is there a way to relate to our audience like how it's explained by the theory, like that it would just be constant, or is that just an assumption that is made and happens to fit observations? Like, does it come from anything else, like that mechanism of like,
Um, yeah. Well, it comes from the uncertainty principle.
hmm,
Yeah, that empty space should have of uh, this minimal amount of fluctuation, this minimal amount of like vibrations, if you like. Um, and because it's intrinsic to empty space, it doesn't dilute. The theory says that every square foot of empty space will have this amount of vibration, and so if you double the amount
hmm.
of empty space, each region still has the same amount of vibrations. That's theoretically pretty sound.
Oh, wait, okay, so want to, maybe this will be going a little bit technical, but I'm just for my own curiosity. So like there's the position momentum version of Heisenberg uncertainty principle, or position velocity, depending on your perspective. And there's also an equivalent energy and time, that like in a certain delta of time, there can be like a certain delta of energy created out of empty space as long as it's repaid back. Like you can have particles pop in and out of existence,
Yeah.
and so that creates energy, but also destroys energy in a small amount of time. So my question being is like, where in that does it say that the like, the energy like density of space, empty space in quotes, is like is the same? Like where is that? Where do I find that?
Um, well, well, if you think about it, like let's say that the energy of empty space did dilute
Hmm?
as you stretched it out, then
Yeah.
eventually the energy time uncertainty principle would go away, right? Because
Is
if you
that?
right, like
Yeah.
so,
Oh,
yeah, so like it's like energy time uncertainty principle says that if you look at a shortened amount of time scale,
yeah.
you can see some fluctuation of energy. But
Yeah.
let's say I stretch that space to infinity,
Yeah.
and that energy dilutes, then you
Yeah.
no longer have that uncertainty of energy, right?
I see. So, but why does it imply constant? Why can't it imply like asymptotically just going to like, to zero or something like that? Because, we have okay, I'm going to try to take the other side of this argument. We have a finite like time range of perception, like
Yeah.
from the time when quantum mechanics was first discovered to like currently our existence right now has been about 100 years or so.
Uh huh.
How do we know like it's not so slow that we haven't like been able to perceive that like for a long enough time that it eventually will like go to zero in some sense?
Well, the uncertainty principles state that there's a lower bound on that, which is Planck's constant. So, are you asking whether
Okay.
like is Planck's constant could be changing? It could be decreasing with
I
time.
I guess maybe I'm not sure what I'm asking. I guess what I'm trying to ask is like, this talks about time, but what does like space have to like do with this? Like the Heisenberg uncertainty principle with energy and time, does, I mean, I know time and space are connected to each other, but I'm wondering like, yeah, it doesn't specify space explicitly. So from a theoretical standpoint, how can you say if the universe expands off to infinity? Let's suppose I take like a volume, some like unit volume of space, and then I expand that out to infinity, but I track that volume as it's expanding. So within that volume, Heisenberg's uncertainty principle still holds, but if I go smaller, it like the energy fluctuations aren't there as much.
Um, Sorry, can you repeat that?
Okay, so the question is like, if I were to have a unit volume, like let's say 1 meter cube volume of space,
Yeah,
and I'd like let that expand at a certain rate, and let's
yeah,
say I can live infinitely long, for instance,
yeah.
and I observe that Heisenberg's uncertainty principle holds true in that volume as it's expanding. Even when it expands out to infinity, it still holds, but it's not like, individual like 1 meter cubes have the same Heisenberg uncertainty principle. It's just that like that region of space that I was tracking
Uh
has
huh.
that.
Well, Heisenberg's uncertainty principle, yeah, it essentially relates. Well, the space momentum, the version of Heisenberg's uncertainty principle gives you that space scale over which these fluctuations
Hmm.
can occur.
Yeah,
Um,
yeah.
and that should stay fixed even if the universe is expanding. The energy time uncertainty principle is a little bit more subtle. It's actually a derived, like that's not like a fundamental postulate actually. That's derived from the space momentum uncertainty principle. Um, but you're asking like, what if I stretch time to infinity, then you could still have very short time energy fluctuations over a large spatial scale, and you could still say that the energy time uncertainty principle holds.
Yeah, I guess it comes back to the original thing, like does Planck's constant like stay constant throughout the cosmos? Because so far like we're looking in our like region of space as it's expanding and have shown that like Heisenberg's uncertainty principle holds in that region, but like that doesn't talk about what's outside. So maybe like it could change possibly on like really, really long distance scales and time scales. I don't know, just kind of like really trying to fill the kitchen sink of like
Yeah,
arguments against this.
yeah. Yeah, so it's like if people, you're saying if people did experiments that's like trillions of years from now, they might
Uh,
they might they might still have something like the uncertainty principle, but it might simply hold over like larger scales of space.
yeah, I guess like I'm just trying to figure out like what is it about the uncertainty principle that tells me that it holds for a unit like a unit volume of some size, for instance.
Uh-huh.
Like when if I go to my undergraduate quantum mechanical textbook, it tells me like energy and time have this like relation, or rather changing energy times change in time follows some sort of inequality. And
Uh-huh.
so my question to you would be like, how do I know that like this holds across like unit volumes of space? Basically, I'm just trying to dig into like where in the theory does it state that like a unit volume of space, no matter how much the universe expands, but that specific unit volume of space will have like a constant energy. I'm just trying to figure out like where is that explained in the theory?
That's not explained in the uncertainty principle itself, but the uncertainty principle basically like the space momentum version of it.
Uh,
You can kind of imagine it as like a grid. It kind of sets the distance for what the smallest unit of space can be,
yes.
which is the Planck length.
Uh,
Um, so you could ask the question like, well, does the Planck length increase as you expand space? How do we know that Planck length is not increasing as we expand space?
hmm.
Um, I'm sure a million things would go completely out of whack if we assume that Planck length was expanding with the
Yeah.
universe. Yeah, it would change the scale of quantum fluctuations. It would change the results of you would definitely be able to detect that in experiments.
I see. I see.
Yeah, the spontaneous like pair creation of particles, the rates would be changing with time. Um,
Uh,
and those rates are very closely tied to like star evolution and things like that. So I'm sure like a lot of like early universe astronomy would be very difficult to explain if you assume that the Planck length was changing with time. Um, yeah, Planck's constant is it's a very yeah like I wonder if atoms would even be stable if you imagine that Planck length was increasing with time. Yeah, I don't have a good answer off the top of my head, but
all good, all good, all good. So I recognize we're basically almost at time, and so do you want to give the audience any like parting words before we head out?
yeah, like empty space turns out to be one of the most interesting things. Like in particle physics, you spend almost all of your time just thinking about the physics of empty space. And empty space is really not empty. I think that's a fact that we know to be true beyond a reasonable doubt. So what does that? What kind of life lessons does that impart to us? There's more to the eye than what what it seems. So yeah, I guess that would be it.
I like, I like it. Yeah, I wish there's some witty quote I could pull out for that,
I know
but
there's something, but I just I can't.
uh, empty space is more than what meets the eye. I don't know, something
Everything
like
is more than
that.
what meets the eye, even empty
Yeah,
space.
don't judge a book by its cover is basically what I'm thinking.
But that's why they made covers in the first place.
All right then. Well, I want to thank everybody for joining us, and we'll see you all next week.
Yep. Bye bye.
Bye.
Recording stopped.
Have you ended the stream?
Oh, I should end the stream. Yeah. That was fun. I felt a little bit out of my element, but